Hey everyone, welcome back to Electrical Engineering Bootcamp, where we break down the complex world of power utilities and engineering into bite-sized, easy-to-understand pieces. If you're passionate about the power industry or just curious about how electricity gets from the power plant to your home, you're in the right place. Today, we're diving into a crucial topic that keeps our power grids reliable and efficient: power transmission and distribution equipment asset management. And specifically, we're going to focus on a fascinating aspect of this: contact electroplating. This process might sound a bit technical, but trust me, it's a game changer in maintaining and extending the life of our electrical infrastructure. Silver plating is widely used in various industries due to its excellent properties. It is often chosen for its ability to conduct electricity and resist corrosion. These qualities make silver plating ideal for use in electronics and semiconductors, as well as in aerospace, telecommunications, military, and automotive applications. One of the main reasons silver plating is so valuable is its high conductivity. This means that electricity can pass through it very easily, making it perfect for use on copper wires and other conductors. In the world of electrical power distribution, we often see silver plating on bus bars. A bus bar is a thick strip of copper or aluminum that carries electricity inside devices like switchboards and substations. To make sure the electricity flows smoothly with minimal resistance, the joints where these bus bars connect are often coated with silver. Silver plating also offers a surface that can be easily soldered, which is important for creating strong and reliable electrical connections. Its corrosion resistance means that it can withstand harsh environments without degrading, ensuring long-lasting performance. Additionally, silver plating can be used for engineering coatings, bearing surfaces, and applications that require anti-galling properties, which prevent parts from sticking or wearing out prematurely. To ensure the highest quality and performance, silver plating must meet certain standards. These include MIL QQS 365D and ASTM B700 in the United States, as well as ISO 4521, which is an international standard for metallic coatings. These standards help guarantee that silver plating is applied correctly and will perform as expected in various industrial applications. Silver is a great material for many uses because it doesn't react with oxygen in the air. However, it does react with sulfur compounds, which are found in many industrial and urban environments. These sulfur compounds cause silver to tarnish, which means it starts to change color. Tarnishing can happen in different degrees, from slight yellowing to a dark brown or even black color. When silver tarnishes, it often turns a light yellow color first. This slight yellowing doesn't affect the silver's ability to conduct electricity, so in many cases, it's not a big problem. But if the tarnishing continues, the silver can turn a dark brown or black. This discoloration can cover just part of the silver or the entire surface, depending on factors like how the silver is stored or if it has been handled a lot. Even though tarnishing mainly affects the appearance of silver, it can also have practical implications, especially for electrical components. When silver tarnishes excessively, it forms silver sulfides, which are unstable at higher temperatures. This instability can impact the performance of electrical connections. Silver possesses several technical properties that make it highly useful despite its tendency to tarnish. Firstly, it has a remarkably low electrical resistance. This means that electricity can flow through it with minimal hindrance, making it an excellent conductor. Additionally, silver boasts a high electrical conductivity, which positions it among the top materials for conducting electricity efficiently. In terms of hardness, silver falls within a range of 70 to 160 HV, high voltage, indicating that it is relatively soft compared to some metals but still durable enough for many practical applications. Its melting point is relatively high at 960 degrees Celsius, enabling its usage in environments with elevated temperatures. The thickness of silver plating is crucial because it affects how well the silver can protect the underlying metal and perform in different environments. If the plating is too thin, less than 2 micrometers (μm), it tends to be porous, which means it won't protect the base metal from corrosion effectively. For various industrial applications, particularly those where the equipment faces corrosive conditions, the thickness of silver plating should ideally fall within the range of 2 to 40 micrometers. This range is crucial for ensuring the effectiveness of the plating under different circumstances. Thin silver plating, approximately around 2 micrometers thick, is typically utilized for contacts that are bolted together within a factory setting and are not frequently exposed to the public. These thin layers are often applied to copper contacts, as they offer sufficient protection while also being cost-effective. On the other hand, thicker silver plating, at least 5 micrometers thick, is recommended for contacts that are assembled on-site. This thicker layer ensures that the contacts can withstand the additional handling involved in on-site assembly and potential exposure to harsh environmental conditions. Moreover, a thickness of at least 5 micrometers is necessary for plating on aluminum, aluminum alloys, and ferrous, iron-based, alloys to provide adequate protection and maintain conductivity levels. Having the right thickness of silver plating is essential for several reasons. Firstly, it ensures that the underlying metal is protected from corrosion, which can damage the equipment and reduce its lifespan. Secondly, thicker silver plating improves the electrical conductivity of the contacts, making them more reliable in transmitting electrical currents. Lastly, proper plating thickness helps in maintaining the mechanical integrity of the contacts, preventing wear and tear during use. When silver is plated directly onto a surface, particularly one made of copper or copper alloys, issues can arise. These problems include tarnishing, diffusion of base metals, and even blistering at high temperatures. To combat these issues, it is recommended to use a nickel underplate of at least 1.25 micrometers (μm) thick underneath the silver plating. A nickel underplate acts as a barrier, preventing copper or copper alloy elements from reaching the surface of the silver. Without this barrier, copper can diffuse through the silver, especially at high temperatures, leading to oxidation and tarnishing. This process can cause the formation of a tarnish film that changes the properties of the silver surface. Additionally, without a nickel layer, oxygen can diffuse through the silver to the copper base, potentially causing blistering. Nickel also prevents the formation of weak silver-copper intermetallic compounds at temperatures above 150 degrees Celsius. These compounds can create adhesion problems, making the silver layer less durable and effective. When a nickel underplate is applied before silver plating, the thickness of the silver layer usually begins at 2 micrometers (μm) or more. However, the exact thickness required depends on several factors. Environmental conditions play a significant role. Harsher environments may demand thicker silver plating to ensure durability and protection against corrosion. Additionally, the temperature the plated item will be exposed to influences the necessary thickness. Higher temperatures or longer exposure times may require thicker layers of silver to maintain integrity. The durability requirements of the application also affect the thickness needed. More demanding uses may necessitate thicker silver plating to withstand wear and tear over time. Furthermore, any surface treatments applied before plating can impact the required thickness of the silver layer. Certain treatments may necessitate thicker plating to ensure adequate coverage and protection. The presence or absence of a nickel underplate is another critical factor. If a nickel underplate is not utilized, a thicker layer of silver is typically required. This compensates for the lack of protection against substrate corrosion and diffusion provided by the nickel underplate. In summary, determining the appropriate thickness of silver plating involves considering various environmental, temperature, durability, surface treatment, and underplating factors to ensure optimal performance and longevity. Using a nickel underplate and ensuring the proper thickness of silver plating not only protects the base metal from corrosion and tarnishing but also enhances the overall durability of the electrical contacts. Thicker silver layers provide more material between the substrate and the environment, leading to more wear cycles and a longer lifespan before any base material is exposed. Hey there, engineering enthusiasts! If you're enjoying our videos and looking to dive deeper into the world of power utilities, I have something amazing to share with you. I wanted to bring you an exclusive course titled, Physical Asset Management Fundamentals for Electrical Engineers. This course is designed to give you core fundamental knowledge in effective strategic decision making throughout the asset lifecycle, just like in the utility industry. This course covers everything you need to know about managing physical assets, from planning and procurement to maintenance and decommissioning. It's packed with insights that will help you make smart, strategic decisions to maximize efficiency and reliability in your projects. Whether you're a seasoned professional or just starting out in the field, this course will equip you with the essential skills to excel. Don't miss out on this opportunity to boost your expertise and advance your career. Click the link in the description below to check out the course and get started today. Trust me, you won't want to miss this. When plating silver onto different base metals, it's often necessary to use an underplate to ensure the silver adheres properly and to enhance corrosion resistance. The type and thickness of the underplate depend on the base metal being used. This step is crucial to make sure the silver layer stays in place and performs well under various conditions. Different base metals require different underplating materials and thicknesses. For instance, when plating silver onto copper, a layer of nickel might be used as an underplate. This helps prevent issues like diffusion of the base metal into the silver, which can cause tarnishing and weaken the overall plating. The exact specifications can vary, so it's important to follow guidelines specific to each type of base metal. One challenge with silver plating, especially in environments where sulfur is present, is tarnishing. Tarnish is a layer that forms on the silver surface, changing its appearance and sometimes affecting its performance. To combat this, an anti-tarnishing treatment is recommended. However, for electrical applications, not just any treatment will do. To choose the right anti-tarnishing treatment, it needs to meet specific standards. Firstly, it shouldn't contain lacquer since lacquer can mess with how well electricity can flow through. Secondly, the treatment shouldn't change the color of the silver. It's also important that the treatment can be easily removed without messing up the silver layer. Lastly, the treatment has to follow rules about reducing hazardous substances, like not having harmful stuff like hexavalent chromium, CRVI, according to the RoHS guidelines. Luckily, there are options out there that don't have chromium and still tick all these boxes. These chromium-free solutions are great for keeping silver-plated parts safe from tarnishing while still making sure they meet safety standards. Using the right underplating and anti-tarnishing treatments ensures that silver-plated components remain functional and visually appealing over time. By adhering to these guidelines, we can protect the base metals, maintain the conductivity of the silver, and extend the life of the plated parts. Silver plating is a versatile technique used to enhance the surface properties of various metals. According to the ASTM B700 standard, silver coatings can have different finishes: matte, bright, or semi-bright. These coatings are chosen for their ability to be easily soldered, their excellent electrical contact properties, and their high thermal and electrical conductivity. Silver plating also offers good wear resistance and excellent reflective properties. Silver coatings are categorized according to three primary criteria. Firstly, purity is a crucial factor, referring to the minimum level of purity of the silver utilized in the coating process. Secondly, the appearance of the coated surface plays a significant role in classification, with options including bright, semi-bright, or matte finishes. Lastly, surface treatment after plating is considered, determining whether any additional treatments have been applied to the surface to enhance its properties or appearance. Before applying the silver coating, the base metal undergoes several preparatory steps, such as stress relief, a strike layer, and underplating. After plating, the silver may also need embrittlement relief to enhance its durability. Silver plating can range in appearance from a white matte to a very bright finish. The corrosion resistance of the plating can depend on the type of base metal used. The hardness of the silver plating can vary, typically between 90 to 135 Brinell, depending on the specific plating process and conditions. One of the key advantages of silver plating is its excellent solderability, although this can decrease over time. Silver also has great lubricity, making it useful for applications that require anti-galling properties, such as static seals and bushings. According to the MIL QQS 365D standard, the minimum thickness for silver plating should be around 13 micrometers, μm, or 0.0005 inches, unless specified otherwise. Silver is an excellent conductor of electricity, which is why it is widely used in electrical contacts and joints, such as those in switchgear assemblies. Common methods for silver plating contact surfaces include electroplating and dip immersion processes. For copper or aluminum busbars, a silver plating thickness of 5 to 15 micrometers is usually sufficient. However, thicker coatings might be necessary in harsh environmental conditions due to the porosity of silver plating. For disconnect switches, the plating must be thick enough to prevent the base metal from being exposed to contaminants, as these joints will be frequently connected and disconnected over the equipment's lifespan. While silver plating offers many benefits, it does have some drawbacks. One significant issue is the risk of galvanic corrosion when silver-plated aluminum or copper is connected. Since silver and copper are cathodic to aluminum, this can lead to corrosion of the aluminum. It's important to consider this potential problem and take steps to mitigate it in applications where such connections are necessary. Tin plating is a popular choice for coating various metals because it offers a cost-effective and reliable alternative to more expensive finishes like gold and silver. Tin has several advantages, including low cost, low contact resistance, CR, and excellent solderability. This makes it a preferred option in many industries for different applications. The quality and characteristics of tin plating are guided by various standards. These standards include MIL T10727C, known as tin, which sets out the requirements specifically for tin plating in engineering applications. Additionally, ASTM B545, or the standard specification for electro-deposited coatings of tin, details the specifications for coatings of tin deposited through electroplating. Furthermore, ISO 2093-1987, titled Specifications and Test Methods for Tin Electroplated Coatings, offers international guidelines for the specifications and testing procedures related to tin electroplated coatings. Tin plating offers several significant benefits, making it a preferred choice for many applications. Firstly, it provides corrosion protection for the base metal, thus extending the lifespan of the component. Secondly, tin exhibits excellent solderability, allowing it to easily bond with other metals during soldering processes. This characteristic is particularly advantageous in electronics, where reliable electrical connections are crucial. Lastly, tin plating enhances the anti-galling properties of the base metal, reducing the likelihood of parts sticking or wearing out during use. This makes it valuable for various mechanical applications where smooth movement and durability are essential. For certain base metals, especially copper alloys containing more than 5% zinc, it is recommended to apply an underplate of copper or nickel before tin plating. This underplating ensures better adhesion and enhances the overall performance of the tin coating. Tin plating is widely used in various industries due to its versatile properties. For instance, in the electronics industry, tin plating is used on circuit boards and connectors to ensure reliable electrical connections and easy soldering. In the automotive industry, tin plating protects metal parts from corrosion, ensuring they last longer even in harsh conditions. Tin plating is categorized into two main types, outlined in the Tin Military Standard MIL T10727C. Type 1, which involves electrodeposited plating, and Type 2, where tin is applied through hot dipping into molten tin. Typically, tin plating appears gray-white and has a soft but highly ductile texture, meaning it can stretch without breaking easily. It also boasts good corrosion resistance, often meeting requirements such as enduring a 24-hour exposure to a 20% salt spray test. However, tin isn't suited for very low temperatures below -40 degrees Celsius, -40 degrees Fahrenheit, as it can undergo structural changes and lose adhesion. Despite its advantages, tin plating does have limitations, notably in terms of durability and susceptibility to fretting corrosion, a type of wear that occurs at contact points. To mitigate these issues, it's advisable to limit the use of tin plating to applications with fewer mating cycles. Additionally, employing appropriate contact design and lubrication can help reduce the risk of fretting corrosion, ensuring the longevity of the plated parts. Understanding the technical characteristics of tin plating is crucial for selecting the appropriate type for various applications. Tin layers typically exhibit a hardness ranging between 20 to 27 HV and have a melting point varying from 205 to 232 degrees Celsius. Its specific electrical resistance is approximately 115 × 10⁻⁹ ohms. Indicating its conductivity. The coefficient of linear expansion, which shows how much tin expands when heated, ranges from 17 to 27 micrometers per degree Celsius. Moreover, tin demonstrates excellent electrical conductivity, reaching up to 8.7 × 10⁻⁶ ohms (-1 meter (-1) at 20 degrees Celsius. These characteristics help in determining the suitability of tin plating for specific engineering needs, ensuring optimal performance and durability. In the subsequent section, we will delve deeper into the challenges posed by tin plating, particularly focusing on fretting corrosion and effective mitigation strategies. Since July 1, 2006, the RoHS directive has been in effect, banning the use of lead in products. This means that manufacturers need to switch to components that comply with RoHS standards. Some manufacturers are already suggesting using pure tin or high tin content surface finishes instead of lead-containing tin. However, there's a big reliability issue with these finishes. Pure tin plating can lead to tin whiskers, which are tiny filaments that might cause short circuits in electronic components like connectors. Different types of tin plating are used. These include matte tin, tin copper alloy, SNCU, bright tin, and hot-dipped tin and tin copper. Usually, these platings come with a nickel underplating, which helps improve their performance and durability. Electronic components with a lead frame often get plated with matte tin alloys containing a bit of bismuth, Bi, or silver, Ag. When it comes to tin plating, sometimes an underplating is used, sometimes not. But for electronic components without a lead frame, it's common to use nickel underplating. And it's recommended to do a post-baking, which is basically heating the plated component at 150 degrees Celsius for an hour. Other types of platings used for electronic components include hot-dipped tin, tin silver, snag, tin copper, SNCU, and reflowed tin. Understanding these different plating options and the considerations for RoHS compliance helps ensure that electronic components are not only safe but also reliable and long-lasting. In the next section, we'll delve deeper into the challenges and solutions related to tin plating in electronic components, exploring ways to enhance reliability and performance while meeting regulatory standards. The thickness of tin plating depends on the base metal it's going to be applied to. When electroplating tin onto copper, it's recommended to have a thickness of at least 5 micrometers. For aluminum, the recommended thickness is a bit higher, around 8 micrometers. To meet the requirements of the RoHS directive, which aims to restrict hazardous substances in electric and electronic equipment, including replacing lead in tin lead coatings, there are some lead-free alternatives to consider for electrical applications. These include tin bismuth alloy, SNBI, tin copper alloy, SNCU, and tin silver alloy, SNAG. Alternatively, pure tin, either matte or bright, as well as silver or nickel plating, can also be used as substitutes. However, it's important to note that pure tin plating doesn't protect against tin whisker growth and fretting corrosion. Nickel plating isn't typically used as the main coating for conductive parts in electrical equipment. Instead, it's more commonly applied as an undercoating for other metals like gold, tin, or palladium. Its primary role is to act as a barrier layer, preventing the base metal from diffusing to the surface. For instance, when used with tin-coated contacts, nickel plating helps prevent the formation of copper-tin intermetallics. One of the advantages of nickel plating is its ability to passivate pores and bare edges. This means that it helps reduce the potential for pore corrosion and creep corrosion, which can weaken the metal over time. By providing a protective barrier, nickel plating contributes to the overall durability and reliability of the coated components. In real-world applications, nickel plating plays a crucial role in enhancing the performance and longevity of various metal components. Whether it's serving as an undercoating for other metals or providing protection against corrosion, nickel plating is a versatile and valuable technique in the realm of surface finishing. In the electrical industry, nickel plating finds unique applications, especially when it comes to aluminum components used in wires, cables, and terminal connectors. Sometimes, in industrial settings, metals need a little tweaking to ensure they make good and long-lasting electrical connections. For instance, in the aerospace industry, nickel electroplating on aluminum has proven to be a fantastic way to boost the surface conductivity of the material. While traditional methods of nickel plating on aluminum can be pretty complex, involving chemical pretreatments and multiple layers, there's a newer and simpler method that's been developed. This direct nickel electroplating method only needs 2 steps to coat the substrate. The resulting nickel layer not only sticks well but also meets electrical contact standards. Plus, it's stable even at high temperatures, around 400 degrees Celsius. Studies have also shown that when fretting, a kind of wear at contact points, messes with the properties of nickel-plated aluminum. Using lubricants and heavier loads can help mitigate the damage. Nickel plating has been put through the paces, even on copper bus bars bolted to aluminum. And guess what? It showed excellent stability and started off with low contact resistance. In fact, tests have shown that nickel-plated copper to aluminum connections perform better than those plated with silver or tin, no matter the conditions they're put through. Nickel plating isn't just for aluminum. It can go over a bunch of other metals too, like steel, brass, and copper. Sometimes, before the nickel plating process, metals need a little prep work, like immersion treatments or pre-plate deposits. And if it's aluminum, it needs to go through a process called immersion zincating first before it can get plated with either electrolytic or electroless nickel. Understanding these processes and their applications helps ensure that electrical components are not only functional but also reliable and long-lasting. In the following section, we'll delve deeper into the specifics of nickel plating, exploring its various uses and advantages in different industries. I want to share with you an incredible resource that's perfect for job seekers in our field. The Job Board for Power Utility Job Seekers. This job board is dedicated to helping you find the best opportunities in the power utility industry. Whether you're an experienced engineer, seeking a remote position, or looking for an internship to kickstart your career, this job board has got you covered. It's packed with listings tailored specifically to our industry, making it easier than ever to find your dream job. Don't waste time sifting through generic job sites. Head over to the Electrical Engineering Bootcamp Power Utility Job Board and discover a wide range of opportunities that match your skills and interests. Click the link in the description below to explore the job board and start applying today. Your next career move is just a click away. Nickel plating comes with some defined properties, and you can find them in Federal Specifications QQN 290A, 1997, and SAE-AMS QQN 290, 2000. These specs cover what's needed for nickel plating on different metals like steel, copper, zinc, and their alloys. Nickel plating, as per these specs, falls into two main classes: Class 1, which is all about corrosion protection, and Class 2, which is more about engineering needs. Class 1 nickel plating has 7 grades, each with different thicknesses. It ranges from Class A with the thickest plating, about 40 micrometers, to Class G with the thinnest coating, around 3 micrometers. According to these specs, Class 1 plating should be on top of a layer of copper for steels and copper-based alloys. For zinc and zinc-based alloys, it needs to sit on a layer of copper or yellow brass. And if a copper alloy has a lot of zinc, like 40% or more, it should have a copper underplate of around 7.5 micrometers. Within Class 1, there are 3 processing grades: SB, which means a single-layer coating with a super shiny finish; SD, which also has a single layer but with a dull or semi-shiny finish and contains less than 0.005% sulfur; and M, which stands for multi-layer coating, either double or triple layers. When nickel plating is applied on copper and copper alloys with a thickness of 5 to 20 micrometers, it helps protect them from corrosion, whether they're indoors or outdoors. For aluminum and its alloys, nickel plating needs to be a bit thicker, around 10 to 30 micrometers, to provide the same level of protection. Before nickel plating on aluminum, it's recommended to first immerse it in zinc or tin plating and apply a layer of copper or other undercoatings to make sure the nickel sticks well. Electroplated nickel is a popular choice for coating copper conductors, and there are quite a few standards out there that define how thick this nickel plating should be. These standards, like ASTM B3, ASTM B5, ASTM B170, ASTM B286, ASTM B355, MIL W16878, MIL W22759, MIL W27038, and others, help ensure that the plating is just right depending on the size of the conductor. Nickel-plated copper has a ton of uses, especially in tricky spots where wind and moisture could cause problems, like in aircraft wiring. It's also great for safety wiring in aircraft engines and fire-prone areas, keeping things running smoothly. And it doesn't stop there. Nickel-plated copper is handy in automotive engine and exhaust monitoring, high-temperature industrial gear, home appliances, electronic gadgets, electric furnaces, heat tracing wiring, and even down-hole oil logging. The cool thing about nickel-plated copper is that it brings together the best of both worlds, the superconductivity of copper, which helps electricity and heat flow efficiently, and the tough, corrosion-resistant nature of nickel. Bare copper wires are fine for military stuff up to around 105 degrees Celsius. But crank up the heat, and they start to oxidize and get brittle, losing their flexibility and conductivity. That's where nickel plating comes in. With different thicknesses of nickel, the copper wire can handle way higher temperatures, up to a toasty 450 degrees Celsius, that's 842 degrees Fahrenheit,